The electric system, there are many applications for doing something using the electric circuit. So, in generally, and in the most frequently used, this electric circuit system is a kind of a filter. For example, we have a filter like this one. This is a filter. We have inserted some signals in this manner, and we get some results. We insert the input in this manner. Then there are several typical filters. For example, we want to get only the very steady variables from the source. I mean, we call that is a low pass filter. I'll give you an example. Low pass filter. I mean, the low frequency signal. It could be power, but anyway, in general, we use the signal. It's going to the system filter. We call this is low pass filter. Then output is a low frequency in the signal. But high frequency signal go to this low pass filter. Then the signal, there are no signals. This is kind of a low pass filters. I mean, in other filter, for example, high pass filter, or band pass filter, or band stop filter. That is the most of them is kind of a filter. It's general filters. But I will give us some example of low pass filter here. Select that. The example, especially with a passive low pass filter. Generally, the passive low pass filter, there are several. The configuration of the passive low pass filter. This is is kind of one of the kind of them. There are one inductor, and there are register here. Something like that. And we insert here the signal is a V in. The time domain here, and we measures these voltages. We call this as V out voltages. I mean output. Then what's the meaning of that? To solve the relationship between the input and output, I will replace this with the pager. This really pluses J omega L. Okay, this is L, R, this is R, then this will be V in, this is a V out, the pager. Then we get a solution here. So now V out will be R plus J omega L and R. V in. Okay, right. V out omega is a V in omega. We need to think about this. For example, For example, let V in is as a V, A. Okay, I can use a notation of A cosine 2 pi 0.00001 t, this manner. I mean, this is a very, what's the meaning of that? Very low frequency. Then, how about the outputs? In this case, omega is, okay, I don't want to make a complicated problems. So, I mean, 0.0000001 t. So omega is -7. So from here, we get the VO omega is R plus J L R V int. These are very small values, right? So we neglect these terms. So this will be about R V in. Therefore, this will be V int. So in the very low frequency, V out is the same with the V in. That means this filter passes the input to the output directly. How about very high frequency? A cosine t. Then VO omega will be R, in this case, this is a very high frequency. Omega is, then that will be J7L V in. Actually, we need to define the R and L values, but let the R is 1 and L is 1. Then the magnitude of that is very huge compared to here. So it could be about, we'll let R is 1, L is 1, then that will be 1 plus J 10.7, and this 1 is V int. That is very huge, so it will be 0. What's the meaning of that? If input it has a very high frequency, then output is 0 and no output. That means high frequency signal is stopped by the filter. So this characteristic is dependent on, this is a function of frequency. Generally, in the electric circuit has a frequency response. There's kind of a function of frequency. I mean, output is dependent not on the input variables, but also the frequency of the input. So this is very important. And especially, the system can be represented in the frequency. It's omega. It looks like that. This is a frequency response. So from this frequency response, we can guess that this is a low pass filters, high pass filters, band stop filters, band pass filters, or other something. So if you have a time domain signal system, then you can guess. You need to guess the output of the system according to the inputs in very, very single inputs. But in the viewpoint of the frequency, you does not know about what is the input and what is the output. Just to look at the system transfer function or system's frequency response, you can guess the behavior of the system exactly. So that's the reason we discuss about the frequency of response in this time. So we call this is low pass filters. I mean, the system has a different behavior according to the frequency, low and high. So I will give you in more detail. So here, in this system, we have a more exact description. H omega was input and output. So that was R plus J omega L. So the same, because this is a frequency response, or you can call the network functions. So you need to make a form in different forms. In this manner, then you can change this 1 plus J omega L divide L. So this can be rewritten 1 plus J omega 0. So here omega 0 was LR, and we define this is H0. H0 is 1. Here, no, I will write again. So this is a general form of low pass filters. Actually, that is get it, H omega was H0 1 plus J omega 0. So there are two parameters. That was H0 and omega 0. And from here, we can calculate the gain of this. The gain is magnitude of H. So from here, we can calculate H0 and the magnitude of this 1 plus omega 0 omega square. That's our gain. And we can do that as page shift. So that is the two variables. The page angle of H0 minus page angle of this. So this page angle is arctangent omega 0 omega. So this is the general form of the page shift. So in some case, for example, but if here omega is very small compared to the omega zeros, then what happens? The gain will be 1 plus omega 0 omega square and H0's magnitude. And because this is very huge, so we're going to go to the 0. So the main thing is H0. So because of that, we call this as a DC gain. What's the meaning of that? This means very, very, very low frequency. I mean, frequency is 0. So we call this as H0 is DC gain. And how about the omega 0? We call omega 0 is half power the frequency. It's in low pass filters. I'll give you this again. This is another form of the low pass filters. Then let if V in is a cosine omega t, then what is VO? VO will be the H omega V in omega. And H omega is H0 is 1 plus J omega 0 omega, and V in is a 0 degree. So we get it. The magnitude of that is H0 magnitude and 1 plus omega 0 omega square, and phase angle is, because the left H0 is a real numbers, then that will be minus arctangent omega 0 omega. So this is this and a 0 degree. This is input signals. So we can rewrite that is 1 plus omega 0 omega square H0 actually is a number here, and we have a, and phase angle is minus arctangent omega 0 omega. Oh, actually I'm long inconvenience than here. So now we make we change this is 1 plus omega 0 omega square, and we change the magnitude of H0 and A, and we have phase angle is H0 minus phase angle arctangent omega 0 omega. So from here we get it that this is a VOT time domain. This is a magnitude and this is a phase angle. So magnitude was H0 and A and 1 plus omega 0 square omega square cosine omega t and minus arctangent omega 0 omega plus page of H0. That's a time domain response of the system. So how about the power? I mean, if there are some power in the R, I mean, And because this circuit, generally this circuit has like that. This circuit is inductors and resistors this manner. So if this is R, then the power average of this is, the powers consumed by this R is V square R. And because these are peak values, this is RMS. If we replace that is using the peak values, then there will be half V values and R. So because this is the peak values, so we insert here, and then the result was half 1 over R 1 plus omega 0 square omega square and H0 square and A square. So this will be power consumed by R. So from here, have very low frequency. Omega is very small, omega 0. Then average power consumed by R, because omega is very small, so that was half 1 over R H0 square A square 1 plus omega 0 square omega square. That's it. So omega is very small, so this is very small, so this is 0. So then the result will be H0 square and I square. But at frequency, omega is exactly the same with omega 0. Then what happened? It will be half 1 over R 1 plus omega 0 omega square H0 square A square. So because this is 1, therefore 1 over 2 1 over 2 1 over R H0 square A square. So exactly half at omega is omega 0. Therefore we call omega 0 is a half power frequency. So omega 0 is called half power frequency. In generally, this half power frequency at omega 0 is called only low pass filters. This is apply only the low pass filters, especially the first order low pass filters. This term is available when the first order what's the first orders? And the first order means, that in this low pass filters, what is the things? The frequency response. There was 1 of J, omega 0, omega, and H. And here, this is a pole, and this is a kind of a function of J omega's first order. If 1 plus J omega 0 omega 1 plus J omega 0 2 omega, then there will be some H. Then there are 1 and 2s. So we call this is a J omega's second order system. So the omega 0, this term is, we call this as omega 0, but especially we call this a half power frequency. But this half power frequency is available when the system is first ordered the low pass filters. I will give you to explain why we call this is half power frequency at only the first order low pass filters. So we give some example. So from this, where is it? This is the kind of frequency response. So from this point, we can gather this is low pass filters. And I give you some another example, low pass filters example. But they call this is active low pass filter example. So the active means we use the op amp. When circuit has an op amp, then we call this the active circuit. Here we call this is a passive circuit. Why we use passive circuit? Passive means use only passive element. R and L and C and coupled inductors like that. But if we use the op amp, then we call this as active circuit. So using the op amp, we draw the circuit in this manner. And this op amp, we have a feedback line here, right here, and feedback line and capacitor. This is output, and we have one more feedback line. This is a register and capacitor, and we have only the differential input lines. This is R, and here, and here, and this is input. So we call this is R1, this is R2, and C. And we need to solve the circuit in the viewpoint of the input and output. So first, we define this is I1. Then what is I1? Because this is op amp. When you have op amp, we need to define that this voltage and this voltage is the same. So because it's 0 volt, so therefore this is 0 volt. So I1 is R1 divided by V in minus 0, because this is a 0. So that is R1 V in. And one thing is, because this is op amp, there's no current. So all current I1 flow through capacitors and R2. So V out, in that potential V out is 0 minus this impedance and I1. That is R2 and minus J 1 over omega C in parallel and I1. And now the R2 parallel minus J 1 over omega C can be rewrite here minus J omega C R2N R2 minus J 1 over omega C. So you can apply it here. So Therefore, the V0 will be minus R2 minus J1 over omega C minus J omega C R2, and I1 is depth variables R1 V in. So we rewrite here is more simply R1 R2 and minus R1 omega C and J omega C R2 V in. So therefore, we get it the frequency response that was V out divided by V in. That's it. That's it. So we write here J omega C R2 and R1 R2 minus J omega C R1. Then we need to make a different form, the general form, and you remember that. General form is 1 plus J omega 0 and H0, remember? So we write here in this form. To do that, divide by R1 R2. So that will be first we need to multiply by J here. So at first we multiply the J here and J here. Why? Because we want to make a plus J here. So to do that, we make it then R1 omega C plus J R1 R2 and minus omega C R2. Then replace that is because we need to make a 1. So we make 1 this. So what should we do? Then we multiply R1 omega C and R1 omega C. And eliminate in this manner. So the result is 1 plus J R2 omega C R2 and minus R1 R2. So here we need to compare with this general form. The general form is 1 plus J omega 0 omega H0. So what's the H0? H0 is minus R2 over R1, and omega 0 is 1 over R2C. So I mean, in this case, if we design the R2 is R1 higher than R1, for example, design R2 is 10 kilo ohm and R1 is 1 kilo ohm. Then when you DC signals and omega is 0 radian per second, then what's that? Then H0 is DC gain will be minus 10 and 1 is minus 10. What's the meaning of that? If input is 10 volts, I mean, if V in is 10 volt, then V out will be minus 100 volts, because this is minus 10 times higher because of this. So the active low pass filter, because this is low pass filters, the high frequency can rejected by the pass in the filters. But when you pass the signal like DC gains, you make DC gain is higher than 1, like 10, 100, or 5, 2, whatever it is. In the same manner, you can reduce the DC gains very small. So this is the advantage of the active filters. But how about the passive filters? Passive filters, the DC gain is, the maximum DC gain is 1. So in the case of passive filters, we can amplify the signal, output signal compared to the input. But if you are using the active circuit, using the OP amp, then you can amplify your signal levels based on the input. So we call this is the reason. This is the reason we use the active filters. Chapter 13-3, body plot. This chapter is very important because the body plot is very, very useful and very, very powerful. Okay, this is very powerful. Very powerful tools. Not only the analysis of lattice circuit, but also all every circuits. So body plot is one of the most frequently used in the engineering process. So the definition of body plot is exactly, the definition of that is this is a log scale graph of frequency response. So this is, we already discussed about what is the frequency response or the network functions. The network function describes the system characteristics according to the frequency. Especially the system characteristic can be represented with the gains and the phase shift. But the gain and phase shift is a function of frequency. So the frequency response show us the system's characteristic according to the frequency. So that is the equations, but we want to know the characteristic in one site using the graph. That's the reason we use the body plot. So to do that, because body plot is the log scale graph, so we need to know the unit of the dB. The dB is kind of the unit, but the unit is a little different thing is that we need to transfer the variables in some forms like that. Is 20 and log 10H. You can say this is a dB. For example, we want, we call this as the logarithm gain. For example, we have some values. Actually, some values. That is 0.1. Then I want to express the depth values in the dB. Then you need to change depth values in this manner. Like that. Then the dimension is dB. Then that variable is minus 20 values. If that h is 1, then that value is 20 log 1. Log 1 is 0, therefore it's 0. How about 10? 20 log 10 will be 20. I will give it down. How about 100? 100. We need to transfer the 100 to the dB. Then we insert the 100, put in this form. Log 100 is 40. How about 1000? 20 log 1000 is 16. So where's that? 10 times, 10 times, 10 times, 10 times, plus 20, plus 20, plus 20, plus 20. And that's the mean when you multiply in 10 times, then in the dB scale, the variable is increasing only 20s. We call this is a logarithm the scale. So the multiplier use a dB. Multiplier, because multiplier is a function of the frequency, so the multiplier use this logarithm scale. In the Boolean plot, Boolean plot is the x-axis. This is the frequency, but the scale is low scale. And we have two scales, y-axis 1, and we have y-axis 2. The first y-axis is the frequency's response is magnitude. Gain h, and especially the unit is dB. So actually we represent this is a 220 log magnitude in this manner. And second, the y-axis is a phase angle. Phase angle of the frequency response. Especially that values. That is a degree. Unit of that is a degree. So for example, we have passive low pass filters. Example, passive low pass filters. H is 1 plus j omega 0 omega. That is a general form of the passive low pass filters. So we can express these variables. So in the manner of magnitude of that is 1 plus j omega 0 omega square, and the phase angle is minus arctangent omega over omega 0. So this is a h and phi. Right? Because the h, I mean the frequency response is kind of a phasor. So phasor is a complex number. So there are two variables. When you express the complex number in the polar forms, the magnitude and the phasor. So if you want to draw in graph in the phasor, then we need two axes because there are two variables. What is that? The two variables is magnitude and phase, two variables. Because this is a complex number, but of omega, that is the frequency response. So complex number has two values, magnitude and phase angle. So we want to draw this frequency response. That means we need to draw the complex number. Then we need to draw two variables, this magnitude and phase. So we have two axes, so magnitude and the phase. So Bode plot generally have two figures. The first thing is magnitude, and the second thing is the phase. When you draw the magnitude of the complex number in the Bode plot, we use not the exact h values. Instead of that, we use the decibel values. So we have the passive low pass filter just like that. Then we need to get the gain. We need to get the gain. And gain is h. H will be 1 plus omega 0 omega square, right? And the phase angle is minus arctangent omega 0 omega. So if you want to draw the Bode plot, I mean plot, that means draw gain according to the omega, and also we need to draw the phase angle according to omega. This is a Bode plot, but you need to know that the gain represented by log scale. That means dB. Don't forget it. And phase shift, phase angle represented by degree. So that's the things. That's it. The Bode plot is kind of a tool to draw the complex number according to the frequency, and that's it. But when you draw the gains, you need to use the log scale. When you draw the phase angle, you need to use the degree. So this is quite important. Okay, I will give example no more. So I will use this example here. Okay. First, I want to draw the gains. So to get the gains, we make a logarithmic gains because we need to draw the log scale. So first we get the low gains. That means we need to change the h to the 20 log h. So we insert in this manner. So the variable is 20 log 10h is 20 log 10h was 1 to 1 plus omega 0 omega square. So because this is log, so this is 20 log 10 1 minus 20 log 10 root 1 plus omega 0 omega square. So what is a log 1? That is 0. So the main thing is minus 20 log 10 1 plus omega 0 omega square. So we need to draw these functions because this is a gain. So we need to draw these functions. But it looks very complicated. You cannot draw this figure exactly. So we need to make some approximations. For example, if frequency is very small compared to the omega 0 here, that means very low frequency compared to the omega zeros, then we can rewrite 20 log 10h is a magnitude will be minus 20 log 1 plus omega 0 omega square, but this value is very small compared to this. That will be very small is the 0. So there will be minus 20 log 1, so there will be 0. The unit of that is dB. So what's the meaning of that? What's the meaning of that? 0 dB. That is magnitude of V out and magnitude of V in is same thing. Why? H magnitude of that is what is that? V in, V out. Right? Then we make 20 log, when that value is 0, 10h is 20 log V in, V out. I'm sorry, this is not 0. Okay, this is a 0, right? That means 20 log 10 V out is, what is the meaning of Z0? Is 20 log 10 1. Therefore, that means 1. Therefore, V0 magnitude is same with magnitude of that. That's the meaning of the 0 dB. So in this case, the very low frequency is 0 dB. That means V out is the same with V in, because this is kind of a low pass filters. When the frequency is low, then output, when input is go through to the output. So I mean, but if omega is very higher to the omega zeros, I mean frequency is very high frequency compared to the omega zero, then you need to make different things. The magnitude of the frequency response was minus 20 log 1 plus omega 0 omega square. So in this case, this is a very high values, because omega is high compared to omega 0, so that value is very high compared to 1. So we can ignore that values. So it could be rewritten as 20 log omega 0 omega. We need to make approximation here in square. Then this will go out. So that will be minus 20 log omega over omega 0. So we can rewrite this form is minus 20 log omega plus 20 log omega 0. Okay, we rewrite here 20 log omega 0 minus 20 log omega. So in this case, in this case, we have in this manner, we have in these forms. Then we can transfer that this is low scale in this manner, but it looks very complicated, so we cannot draw the function directly. So we need to make a simplify. So we divide the two conditions. The first, summarize. First, the gain of the transfer function can be represented at first as 0 dB at omega is very small compared to the omega 0, and 20 log omega 0 minus 20 log omega at omega is higher to omega 0. Omega 0 is kind of a function of the system parameters. So omega 0 fixed, the omega 0 frequency, we insert its input. Then we need to draw these figures in a manner. Then how can do that? Okay, we will draw this logarithm scale, the magnitude in the log scales. So to do that, we need to draw something example here. So I'll give example is 20 log 10 h was 20 log 10 omega 0 minus 20 log 10 omega. And omega 0 is a function of a parameter characteristic. It's a given values based on the circuit parameters in R and L. And this is a frequency instead of input. So actually this is a kind of approximation equation here. So we want to draw these equations, but you know that their values is a constant and minus 20 some values. So what's the meaning of that? 20 log 10h is a first order function of not omega, of log 10 omega. So that means we call this is the high frequency asymptotic of the plot. I mean, what's the meaning of that? We want to draw that. Then I want to make some plane here and here. So this is actually log. Actually, it's not exactly log. This is this is log omega, and maybe this will be log 10 omega 1, and this will be log 10 omega 2. Maybe this will be log 10 omega 3. If this is the same length of this, yes, then it's the same though, maybe 10 times in this manner. Okay, anyway, you can do that here. And when you apply the omega 1 to that, then we get some variables. Maybe that will be 20 log 10 h omega 1, and we have another values. Then here, then this value will be 20 log 10 h omega 2, right? And 2 points can be connected in this manner. And the slope is 20 log h omega 2 minus 20 log h omega 1 is, and log omega 2 minus log omega 1. I mean, this is log omega 2 minus log omega 1. This is difference of here. So one division is 10 times one decade. Why? You use low scale frequency. So we call this the high frequency asymptotic of the Buddha plot here. So in this example here, if we use this example, if omega is higher compared to the omega during the point here, so in this case, H omega was 1 and 1 plus J omega 0 omega. They can be represented simply 1 and J omega 0 omega. So the magnitude of this is H omega was 1 omega 0 omega, that was omega 0 when omega is higher to omega 0. So we use the slope here. Okay, slope, we can calculate in this system slope. So that'll be, if it's 1 decade, that will be log omega 1 and omega 2. And this is a 20 log H omega 2 is omega 2 omega 0 and minus 20 log omega 0 omega 1. So then you can read right here is log omega 1 omega 2, and that will be 20 log omega 1 and omega 2. So this is eliminated in this manner. Oh, we have one thing, this is minus, so that will be minus 30 dB per decade. So this is the slope of this form. This is a slope of this form. So especially in these low pass filter cases, this is the slope of the frequency response at high frequency. Then we have two graphs here. What's that? We have two graphs here. And this is a function of this, right? Okay. We have H. H was H was 1 plus J omega 0 omega. Then we make locally the dB scale of H. Then we have two graphs. The first thing is the thing out, and this is the second things. Then you can draw the graphs here. This is a log omega. The dimension is radian per second. Right here. This we can get 10 0. That means 1 hertz. I mean 1 hertz in 1 radians. Times 1, times 2, times 3, times 4, times 5. And this is magnitude of h in this manner. But the unit is not linear. This is a dB. That means 20 dB. That means 40 dB. But let and here in this area the slope is 0 dB per decade. But in this case slope is minus 20 dB per decade. So if let omega 0 is about 10/3 in 10/3, that means in this phase we have this is 0 dB figures. Okay, this is that things. And if omega is zeros, I mean omega is omega 0, let omega 0 is 3 here, then that point is zeros. But the scale is here and here and here. So it can be redraws in this manner. So what is a real? When frequency is low in this area, what is the real solutions? This is right. And frequency is higher, is omega 0, then what is right? This is right. So the final solution of that is this and this. This is a function. I mean the graph of h omega. I mean in high frequency, the following these figures. And low frequency following these figures. Especially the point, the midpoint, then we call this is a high frequency asymptotic line. Low frequency asymptotic line. And we call this as, in Korean is 점근선. 점근선. And what's that? That is 0 is 20 log 10 omega 0 minus 20 log omega. That will be omega is omega 0. We call this as a corner frequency. So in the previous chapter, previous, we call this frequency is the half frequency. But other name of that is the corner frequency. Actually, the corner frequency is more frequently used. And anyway, I told you that the high frequency terms is only applied to the first set of low pass filters, but the corner frequency can be applied to the very higher other the systems. So corner frequency means the two asymptotic line meet at the point. We call that is the corner frequency. So I want to summarize that. Okay, I want to summarize that. How to draw Bode plot, especially the magnitude. To let h is 1 plus z omega 0 omega. Then the magnitude was 1 plus j omega 0 omega. So we can make asymptotically the line is 1 when omega is smaller omega 0. That will be omega 0. So there will be omega is higher than omega 0. Now what should we do at first? Change h to dB. So 20 log h omega was divided 2. First, it's 0 when omega is smaller than omega 0s. And the thing is 20 log omega 0 minus 20 log omega when omega is larger than omega 0. Then how can you do that? Then we can draw the graph. Okay. In this manner. Then this is a log omega, and you can define this is 20 dB and 40 dB, and we define this is a log omega zeros in one dimension. This is a log 0.1 omega 0, and this is log 0.10 minus 2 omega 0 here. So you know because of that there are one line here, and because of that we can draw the line. One more things here and here. And the final thing is this. From the here, this, this, and this. This is the final things. No, this is a this is the final things. Actually, this is a kind of asymptotic graph. So if you make a more exact values here, okay. Actually, this point is here. This point is here. If you want to draw the exact values, then problem is here. Actually, this is right. I mean, here is right. Why? This frequency range is very lower than this, and this will be right. This will be right. Why? This range is very higher compared to the omega zeros. It's right. Our objection is exactly. But the problem is here. We have two assumptions. Omega is very small omega zeros, and omega is very higher than omega zeros. So it's okay. Here is okay. The problem is in this area. Problem is in this area. It's a little bit different. So to check it, we apply the exact values to the body plus here. So to get the exact value at omega zeros, we insert 20 log h omega zero was 20 log 1 plus j omega 0. So that value is 20 log that values. If you use in the calculator, then the result is minus 3.01 dB. So exactly at this point, this is asymptotic graph. Exactly at this point, this is a log omega zeros. We have about that values here, and the amount of this is 3 dB. And the real line is, this is the same, but a little bit different in this manner. And there are some, this is exact line. And exactly, this is the values. So, in the case of the four-star systems, the V out is about their values. V in. At corner frequency. So minus 3 dB is a very important value. Has a very frequently used. I mean, minus 3 dB means the magnitude is reduced about the 0.707. Then the power is kind of the square. So the 0.7 square is 0.5, is half. So half frequency, I mean the corner frequency has the half power the frequency in the case of the four-star system. So this is the way when you draw the body plot in the magnitude, you need to separate the body plot is centered in the corner frequency. When the frequency is smaller than corner frequency and frequency higher than corner frequency, then you make a different the asymptotic lines from the magnitude equations. Then draw each lines and combine them, but the dominant line is this line. These lines. So this is a way how to draw the body plot, especially the magnitude.